Pretty slice.
How was it today?
He's
a big boy.
I finished 3 minutes.
Oh,
that's
He's a big boy, that's fine. And that's the first.
He was close.
That's good enough today.
I've known that guy for a long while.
Yeah.
How long? Hey, 35 years.
He's a doer.
You have to do.
Very slowly.
Yeah, so we have microphones here.
I got my
But the microphone is pick up. No, that's fine. Yeah, you can do whatever you want. Take care of it. Okay, let's go ahead and get started. Good afternoon, everyone. Today we have Dan Zollinger, who is a research engineer at Texas Transportation Institute, and he's also a professor at the Department of Civil and Environmental Engineering at Texas A&M. He's a former president of the International Society for Concrete Pavements from between 2006 and 2010, and his major areas of research include concrete pavement performance, rehabilitation, behavioral design. Let's please welcome Dr. Zollinger.
Very much a pleasure to be here. It's brought back a lot of memories, walking around the campus and the building, and it reinforces the notion, the similarities between College Station and Bryan and Champaign-Urbana. Twin cities, one university, lab facilities that are way displaced. Almost the same number of people in the community. I don't know why it worked out that way, but there is a lot of similarity. It's just kind of interesting to think about that. So I did my PhD work here. It's been over 30 years, and I was just reminiscing how quickly the time flies. And occasionally you have to stick your head up out of the, the work that you're involved with and look around and see what's going on. And I just recently did that, and it's been 30 years. So I don't know what to think about that. But, I thought a long time about what I could say to this group, and I've gone back and forth over the last several days, and I had to tie down a title. So once I tied the title down, that pretty much narrowed me in on what I needed to talk about. But I've been interested in concrete pavements it seems like forever. And as I travel around the country, I'm always watching and looking and seeing how different things are performing. And it's just kind of interesting to see, observe things visually. And when I fly from an airport, if I get a window seat, I'm always looking down and seeing the cracks in the pavement. I'm thinking, what are they doing about that? How did this happen? But one of the things that I kind of got interested in are the interfaces in a pavement structure. And there's actually a number of them. I just want to talk about some of them today and some of the work I've done. Before I get too far, I just want to point out our new laboratory that we have now at A&M. I have wanted to get this for a long time, and now we have it. And it's called the Center for Infrastructural Renewal. It's a facility that's approximately 15 miles from where we were located in College Station, and again, similarities on an former Army Air Base that's been converted and turned over to the university. But we We have just moved into it, and we have very nice laboratory areas now for asphalt concrete materials, for concrete materials. We have, I think, a very interesting opportunity to do collaborative thing. That's the message I want to leave. In fact, I've invited Imad to come up and talk to us some more about what we can do collaboratively. But it's a great facility. It's great to have it. I'm not showing this, but next door is the Tti Building, which is kind of changed its mode of operation since this laboratory has been built. This is under the College of Engineering, and the TTI group is now under that. So that's kind of a reverse of roles. It's really changed things a lot for people. But the items here are just ideas that we have of how we can collaborate with others. And there's several on campus that have moved into the building that we hadn't previously associated with. And so there's a lot of interesting changes happening. And I have now 3 offices. And I have to visit them periodically to just see what's going on there. But anyway, yeah, a lot of exciting changes there for us in this regard. So yeah, we'd love to have you come and visit with us and talk about what the opportunities are. For concrete pavements, and concrete pavement technology has changed a lot as well. But these are generally the types that we deal with. And jointed plane, continuous reinforced, roller compacted is probably the newest one there. It's an old idea, but interestingly, it's being pushed into sort of the urban environment for use. And the thing that's interesting about all these types, I think, is that they all have different behavior characteristics. And I think we need to understand them. And not everybody does. And especially in the general engineering community, I'm kind of a proponent that we should have a separate license for pavement engineering. There's been enough, I mean, how many litigation cases do you have? Or do you need to justify, maybe there ought to be a license for this. That's an idea that we could probably talk about and bounce around, but you know, it's kind of my opinion that the most sustainable version out here is actually a precast slab. And it's, you might wonder why I say that, but it has a lot of potential, and where I think we're just beginning to realize what some of the benefits are of precast paving. But you know, the mechanisms are different, and the way they perform end up being differently in a lot of cases. And sustainability is a real important aspect here. And believe me, I'm a proponent for concrete pavements, but there are some options here that are just simply not a good choice. And I don't say that to the industry very much because they don't like to hear me say that, but I think it's true. So what we're about is understanding how long our structures are going to last, right? This is the perennial question that's been there for years, and I don't know if we still have a good handle for it. But owners want to know, how long is it going to last? How long is the new surface going to, how's it going to work in the climate? How's it going to behave under loads? And can we predict how long it will go? How much life? What's the cost going to be? I mean, these are very pertinent questions. I work with a group now of pavement managers. They do truck terminals. And if you've been to a truck terminal and see the things that go on, it's horrendous. I mean, it's phenomenal that the amount of money and the decisions they make, and I just don't think they have the tools yet. So on the academic side of things, there's a lot of work here, a lot of opportunity for us still there, and it's about this these characteristics. And you know, you see this trend here, and we're all familiar with this. And I've done projects looking at pavement rehabilitation and so forth. And I'm probably going to go way over my time because I'm just talking. But anyway, we'll do what we can. But you know, think about this. You know, this is almost the point of no return right there, I think. And I've worked with agencies that are working down here, and they can never get out of that mode. They can't afford it. That's what they say. We can't afford to do this. And yet, you know, how do we end up there? Villages in Houston, the same thing. These small communities that they have pretty good funding, but they're in the same situation. They come and say, well, what can we do to, you know, upgrade our system? And yet there's portions of it that require a lot of money, right? And then there's no money to do the other things. How do you manage that? I mean, we need some pretty good decision-making tools. I don't know if we have them yet. So I'm kind of talking a little bit about that. And, you know, there's some things on the concrete pavement side that we shouldn't be doing. I came to that conclusion. And I'll just say it, one of them is full depth repair. It's a bad idea. It just doesn't last. And I tell people, if you do full depth repair, you've made a mistake. And that may be kind of shocking. You know, this is supposed to be a good idea. And, but, you know, we put a lot of money in to these fixes to get out of this mess. Wouldn't it be better if we could put more money into noting what the signs are that are beginning to show up? Maybe understand that and then put our resources. I mean, that might be money better spent if we can do that. But I don't know if we're paying close enough attention to that. And it's going to be critical to our economy. It's critical to our infrastructure and maintaining the condition it needs to be in. It affects our lives, our lifestyle, our quality of life. It's all that. And you know, my definition of sustainability is pretty simple. If you can't afford it, you can't do it. I don't know. Well, so at A&M, in our materials area, this is our vision. And I'll talk a little bit about this as we go. But you know, we're looking, and I give credit to Zach Graisley for this term. He came up with the term agnostic models. And these are tools that theoretically can work for any material. And that would help bring a commonality, I think, in the way that we characterize behavior for different pavement systems. But we feel like there needs to be some transparent tools for academia to participate in freely, to share ideas, and help promote the development of performance models and prediction. And this is sort of the genesis of it. And I hope this doesn't go away. I hope that we can continue to try to develop the ideas around the modeling and climatic effects and all those things that come into play. This is an interesting idea, and I'll come back to it, but this is just one type of model that might work. And I'm talking about interfaces today, so I'm talking about how things bond, right? How they stick together, how they come apart. They may be different material types, they may be the same material. But this is an energy-based approach, and I'm not going to elaborate on it because I'm just kind of learning about it myself. But the idea of understanding the potential energies and the kinds of energies that are there to affect crack growth or what have you is what we think is a common ground, if you will, to try to unify the approaches that we take for looking at how pavements perform. Now I'm going to talk about this. This is a concrete pavement, obviously. And let me just briefly remind you of some of the things here. So this is our mid-slab crack. This is what most design methods are focused on today, right? This is what this has always been the emphasis, and maybe they do a really good job, because we don't see a lot of that. There's some, but not a lot. And I'm thinking, okay, well, maybe it's time that we look at another mode of failure here that could be really important. The one I've seen most prevalent is this one. And there's not a lot of good explanation out there as to why that crack comes in. It seems that when you do wheel load stress analysis, you can't justify that crack very well. It's a tough one. And yet we see a lot of it, probably more than the other type. And this is related to it as well. Corner breaks, longitudinal cracks, these are not easily understood. I'm going to talk about that a little bit, but there's another example, you know, of kind of what we see. And this is, they call that a local failure, but I think it's all the same derivative, okay? And I think it's tied to the erosion that we're getting here on the joint. You have to ask yourself, why are we seeing that? Because that seems kind of unusual in a sense, but now this is an image. I was looking on the internet one day, and I decided to zero in on Kimmer, Wyoming. You know where that is? Kimmer, Wyoming. It's in the middle of Wyoming. All right, small community. They have concrete pavements there. So I zeroed in on it just an intersecond. Let's see what we can see. This is what I found. Isn't this amazing? Look at this. This is a city street, probably 6 inches thick, most likely. But look at that crack. Runs all the way through. They've got some mid slab, but they've got a lot of corner break. Look at this. And this is common, I think. It's also unsustainable. You know, what do you do with this? This is a tough problem. That one's a tough problem because the fix requires a full depth repair, most likely, and that doesn't last. So we need to up our game here a little bit. I think understanding the erosion process, and Dr. Dempsey did work on this years ago, and it's still relevant, by the way. That's another one of those things that needs to be brought out. But here it is. This is an ideal image. Look at this. This is a CRC pavement. You can see the crack here. The truck just went by, and look what's coming out. I mean, it's like a, you know, just a well of water there. And this is what we often see. We see a, you know, a discontinuity here. And again, these are tough to fix. It's expensive to address these kinds of things. We've got to do a better job of figuring this out. Now, one thing that I've noticed is a concrete slab tends to end up unsupported around the edges and corners. It's a warping type behavior. I don't think we've realized this as much as we need to, is how persistent this is. It's all over. And depends on what part of the country you're in, but California is notorious for this. Now, what's interesting about this situation, the temperature cycle that we see hardly ever causes that slab to come in contact with the base, hardly ever. And it's so much that it's just a springboard. So yeah, we're gonna get pumping. We're gonna get this hydraulic effect taking place. And I believe there's no such thing as a non-erodible material. I don't believe it. There's just too many instances where well cemented, it doesn't matter if it's asphalt or concrete, it eventually gives up. And when it does, guess what? We can't afford to fix it. Money just isn't there. And so I've been saying, we need to figure out how to make them flat. Now this is why I think precast has such a great perspective about it. It's from the evidences I've seen, talking to people and asking about how these projects are doing. Even with unsealed joints, they seem to be working. It's amazing, I think, the effect this has. So how do we do it? How do we get them flat? You know, what's the answer to that? Kind of an interesting thing. Now, I've done some work in Texas over the years, and these are some cores that we took. And look right here, there's a nice little void, and you know, I ran into this in my PhD work, same thing. And the interesting thing here, look, there's the slab, and there's the interface between the base and the lime-treated layer. And that's where the voiding is. This is just fascinating to me to think about what is happening. But these little granules were pumped into this interface and started to wear that out too. I mean, it's a double whammy after a while. And it's a tough problem here, I think, that we're seeing. Now, again, I've been really interested in curing concrete now because I think it's got everything to do with this, but I hadn't proved it per se. So I worked with the state of Florida for the last several years. They're going to do a test road, by the way, and it's a concrete pavement test road, and it's on route US 301. It's north of Gainesville going to Jacksonville. It's on that kind of a back road up there. But I worked on the calibration. They wanted to calibrate the pavement ME, so I was trying to work on that. And the thing that was interesting, and I could talk forever about this, but you know, we had 13 sites, right? We had 13 sites. We started plotting the cracking and damage relations, right? They're all over the place, literally all over the place. There was no consistency from one site to the next. And I'm thinking, okay, so how are we going to calibrate that? Okay, what do you use there? Let's see, what's that identifying commonality? It just wasn't there. And so I started looking deeper, and what I wanted to do, and it was a little rough, but I tried to back out what I thought represented the set of the slab. And it just became evident that it was different, you know, from site to site. It wasn't the same. And Pavement ME has a thing in there, in the program, where you can change the set. It's minus 10 degrees. They tell you not to touch it. Okay? Not supposed to play with that. But, so we wanted to investigate that, and I convinced the department, look, let's go behind, this is behind their facility there in Gainesville, and they have a really nice test area. You can see their accelerated load device here that they're doing some pretty active work with. And but we cleared this area out, so we built several slabs, and we did some in February and some in October. The February ones were the most interesting. You've been to Florida in February. Very mild, right? Rains a little bit. Temperatures are, you know, varying. It's not bad. It's a pretty pleasant time of year, and ideal curing conditions, right? Supposedly for concrete. But nonetheless, I said, look, I'm going to change the type of curing compound, and I listed them here. Notice on this last one we didn't put any. We left it off. And then we had some different thicknesses, and probably more significantly is the time that we place the concrete. Okay, so 10 o'clock, 2 in the afternoon, 5 o'clock in February is just at sundown. So the sun was headed down, it was getting dark, and we put that concrete in. And then the next morning, it was raining, and so we didn't cure it. So this was perfect fog conditions. You can't get anything better than that, right? Okay, so anyway, we had these things really well monitored. We had instrumentation, you can see here on the corners, and that's what I wanted to look at. I wanted to see how the corner changed. And I'm not going to show you all the data here, but you know what was amazing to me? Every slab had a different response. Every one, every cured regime was different. Now, which one do you think was the worst? What was the worst cured situation? The last one. no curing compound. Ideal fog conditions, guess what? It was the worst. It had the worst warp out of all of them. It was very interesting. What was the next worst? What do you think? 10 o'clock. 10 a.m. placement. That was almost as bad as the no cure. The best one was 5 o'clock. Now, notice at 5 o'clock, we put a wax-based curing and a higher rate, you know, a little higher rate, and it turned out pretty well. The interesting thing is the set was almost zero. I thought, man, how can that be? It was just an eye-opener to see how much effect that curing had on all this. Now, here's the interesting thing is, that's how they put the compound on, was by hand. It was a sprayer, had a, you know, the backpack, that's a weed sprayer. Okay, so, you know, and first when they stepped on it, it was gonna be shooting this way, right? That doesn't work. So we had to practice. So we went to the side and we practiced curing. And I got them to straighten it up a little bit. But what we did was we put planks across here so that they could walk right on it. And it was still lousy. But I knew how much we put down. I didn't know that because we weighed it, you know, and so we have an idea. But this is really critical, uniformity. And most of the time we don't have it. And if we don't have uniformity, then you don't know what you have. And the effects are enormous, as it turns out. Anyway, so one interface between the slab and the environment. That's an interface that there's more to be done. Okay. Here's another one. And I mentioned this one because we have to have this done in such a way that we get enough energy to crack those things, right? Now this is a top-down crack. That's a bottom-up crack. So they're kind of, it's kind of odd how they're working against each other. Now, you know, Pavement ME does top-down cracking, right? You know, I learned about Pavement ME, and my impression is if you get a top-down crack, you shouldn't do that design. It's not a good idea. But enough said about that. But so another interface, getting enough energy to get that to break early. And if we don't, guess what happens? We get cracks other places that are wider. And that's, we know, you know, we know that's not going to work either. So timing, saw cutting, that's an interface. Here's another interesting one. When the concrete is setting, we've got hydration, drying shrinkage, we got moisture, thermal conductivity, thermal expansion, creep strains, strength. We got all that stuff going on. They're all interactive. They're all interactive. What do we do in Pavement ME right now? We skip it, right? We go from 0, we start at 28 days, okay? So we're not even representing this yet. And wouldn't this make a difference? If we understand the history of how the hydration products form, how the porosity forms, how the drying shrinkage forms, I think this is all kind of important. And then here's another interesting interface. That's the aggregate paste bond. What do you see here? Hydrated lime, which is a low strength, you know, it's a low strength hydration product. And we see inevitably, and this is gravel by the way, but we see the cracks going right there and then moving on. And yeah, so that's another, and this is why I think we see a lot of spalls in concrete. And spalls, they're unsustainable too. We can't repair them very well. And anyway, here's what I'm working on lately, reinforced concrete, okay? And what's fascinating to me is the movement between the concrete and the steel. And in this specimen, we've put gauges right out the end here, see? And then towards the center of it. And what I'm trying to do is better represent the bond there. And for the longest time, we've kind of thought that there's a slip anywhere through there, and I've just come to the conclusion that that just isn't the case anymore. And you can see it in these results. Look, this is towards the middle, this is out at the end. There's a big stiffness difference. And this could affect how the cracks come through. Now, this is in Texas right now, Texas CRCP. 12 inches, single layer, very stiff base layer. I was talking to Marshall about this last night. But look, these cracks here, they go all the way through. That's a full depth crack. Goes all the way through, gets to the base, fine, right? These are not, those are cracks as well. And they're stopping in the steel, that's a problem. And I hate to say it, but Texas has got this everywhere because they build CRCP everywhere. And they've done this for years. And now they're finding that they've turned their continuous reinforced pavement into a jointed reinforced pavement, and that's just not going to work. I don't know what the answer is going to be for them.
Rubberization.
I think I'm going to stay clear of it. Okay? I think I'm going to stay clear of that. But you know, I have to say, I have to commend the Beaumont district. Now they're a district in Texas that's over by the Louisiana border. And they're far enough away from Austin that I think they can do what they want. And they did. And the interesting thing is, on this project here, they took this layer out and they put and I was going to show you a picture and I forgot, I'm sorry. But they put an unbound layer immediately under the slab, almost 2 inches thick, and it was more or less a uniform graded crush material. And everybody said they're nuts. They told them you can't do that. The contractor told them this is not going to work. You know, on and on and on. They did 10 miles. They did 10 miles. And I got a phone call from the pavement engineer. He said, what do you think of this? And I said, well, it's an interesting idea. Can I monitor it? You know, I'd just like to watch it. And they said, fine, you know. So we did some FWD work. And then 3 years later, just recently, we got some more data. And I started to summarize it. And this is one of the plots that we got. This is crack spacing. And you notice the average is about 10 feet. Not too good for CRC, right? But look at that. Versus the friction on this interface. There's no relationship. They didn't care. This is the old design, but this is what's going on in Texas. Now the Beaumont section, look at this. They got a distribution of crack spacing. That's what we need. That's what it's got to be. I'm not worried about that pavement. This one, yeah. Another key interface is that sub-base slab interface, okay? That contact there. You know, how much is the friction? How do we characterize the strength? I love that question. And I can't help but think there's a lot of work we can do there. I've done, does somebody say something? Sorry. But I've done some work with fracture analysis, trying to get K2, K1 to see how it compares to some of the numbers I get out of FWD. And that's an interesting comparison. But we've got to try and understand that interface, I think, a little bit. And then Jeff and I, doing some work with the tollway, this is a diagram that you guys put together. I think it's quite interesting. Look at this. Look at this here, these clusters. You know, what's the reason for that? And it's hard to describe it. It's hard to explain it. And yet, you know what? When we put saw cuts in here, we saw cut it, goes away. All that goes away. So I threw this in here just to show the comparison. Now, Pavement ME doesn't do this. I think it needs to. This is a normal distribution of cracking. Average spacing 44 inches, right? Here's the same thing for crack width. Right? We get a distribution of crack width, crack spacing, it's distributed. You know, if we notch it, look what happens. All the variability goes away. Now, Marshall, we were talking last night, and I was thinking about the idea of notching, you know, because you mentioned that, and I'm thinking, you think we could justify the cost? That's a good question. And, you know, you tie that back into the rest of the variance, you know, in the performance prediction, I wonder. I don't know, it's just a thought. And it's just kind of interesting to contrast these things and how they may affect performance. Here's another interface that I have done a lot of work with as well. Joint sealing. Isn't that an interesting topic? Yeah, let's see, I was supposed to animate that thing, and I apologize for that. Let me just talk about it. But this diagram right here, it's covered up a little bit, but I took that out of the LTPP database years ago, and it was rainfall versus faulting, and it was astounding. I just was dumbfounded by the similarity. I thought, what is going on? And you got to come to the conclusion that the joint sealing has never worked. It just flat hasn't worked. I mean, we've made the assumption that it has, I think, but I think we've probably felt for a long time that seals are not keeping water out. Okay. Now, why would that be? Why would that be? We did some test sections again out at our Riverside campus, and I had the industry come in and put it in for me because I'm not I don't do joint seals, but they came in, they did the typical thing, right? Sandblasting, cleaning, air drying, did the whole thing. They put their seals in. We put hot pours in, we put silicones, we did all that. And I said, okay, I'm going to stand back now and I'm going to be able to go and measure the infiltration, right? Right? I tried. Never got a drop of water to go through. Not a thing. I was really frustrated. And I was so frustrated, I finally had to take my pocket knife out and cut it, okay? So I cut it free so I could get water through. But it sort of tells a story. We could get these things to seal. I think it can be done. The question is why doesn't it happen? Now, look right here. This is a pavement right near my house. City street. Look how wide it is, very wide. And look right there. This was 3 months after construction. It started tearing free. Here's another one. I don't know if you can see this. We can't turn the lights down, I guess, too well. Maybe it'd probably help to see this a little bit, if we can. Look right there. That's a bubble coming through the perfectly sealed joint, right? Except right there, it's bubbling up. This was right after a rain shower and water was standing in the seal. It's just kind of interesting to think, we're getting water through. And what do you guys think? If you get water, look at this. This is the Midwest problem, which I won't get into that too much, but what do you think about water that gets through a joint seal? Is it going to evaporate out? Is there a chance that the weather, the wind speed, all that is going to cause that water to evaporate? Yeah, probably not. And so this is really detrimental. It'd be better if we did seal. And some people have made that conclusion. We shouldn't be sealing. Shouldn't be.
Wisconsin.
And that idea is still out there, interestingly enough. Well, so erosion, I think, is one of the things that we've got to pay more attention to. And I've identified at least 3 factors: traffic, the erodibility, and the presence of moisture in the, underneath the pavement. These are things that matter. So I'm interested in modeling, what are the properties here, right? What's the key property? What are models that we can use to represent, that use the properties? And then performance. Can we verify the performance? We got to have a connection, I think, in that way to really make sense of our ability to predict what the long term is going to be. It's nice to be able to have a test that you can run in the lab that'll fit into your model, that you can come back and do whatever field testing and verify the accuracy of it and what your predictability is. I think that is quite valuable. And I think there's some models that we have to do that, others don't. We still need to improve on that. A good one is K-value. Just K-value for, its foundation characterization. We can sort of measure in the field, yes, sort of. Can't do it in the lab at all. But no problem, we design with it. Well, where are we today? This is the familiar PCA method for pumping. Probably still the best that we have. Now, it's not sensitive to material type, but it's got load in there, number of track, those things are in there. Okay, and that was done many years ago, and I'm sorry to say, I don't think Pavement ME advanced it too much. However, I'll give them credit. They put number of wet days in it, okay? But how do they define wet days? Pavement ME says, and they're not that far off. They just say if it's annual rainfall over 1/10 of an inch, that's number of days. And looking at the LTP database, sure, why not? Because the seals won't work anyway. So just count the rain, that'll work. Well, I suggested this model right here. Now look at the difference. How many coefficients? There's number 12, 7, 5, this is full of coefficients. Okay? And there's more coefficients than there are inputs, I would say. That's the first sign that I'd say there's a problem here of some sort. Look, I'm just suggesting that. Look, there's two coefficients here I've got. That one, rho and alpha. Those are the calibration. Okay, and that's what it is. Now, there's the damage, and I'm getting damage based on shear. Shear. Now, I think there's, and Barry, you and I can argue this, right? I think there's a mechanical movement between the layers. Slight. And the more deflection, the more movement there is, right? But it's wearing. It's wearing, and our materials are not meant to wear. Okay? They're meant to take bending and things. So shear stress and shear strength. And how we measure shear strength, that's another good question, isn't it? What can we do to improve that? Well, it's in the model now, so we've got to figure it out, okay? But notice what I'm doing. I'm multiplying the damage by the number of wet days. And I'm saying a wet day is the day that it's wet underneath the pavement. So are the joint seals leaking? How often does it rain? What's the possibility that we're going to get water down there? And is it going to drain out, right? That's a whole different perspective now on pavement drainage. It's all different. And now we're interested in it, actually. And now we do have to have those seals work. They've got to. That's up to the industry to figure out. So, yeah, the rainfall, what's the probability that it's going to get through there and get stuck there and not drain out, right? So that's, what are we doing with the joint seals right now? How's my time here? How much?
Usually 1 hour.
So I can take all of it? I'm just getting started, I'm sorry. No, I'll try and get through this, okay? But look, this is what we do today. And we're supposed to have a width and a depth on seals. Look at this. That's filling no backer rod, okay? And, you know, this is practice today for joint seals. We're doing a little bit of work, just looking at, and this is work done years ago, and we're going back and repeating some of it, but, you know, the stresses generally are in the middle of the seal, where the high ones are. And this curvature is really critical. You know what we do for noise? They fill that up. Visuals throw away the backer rod too, because now you've increased the stress level here more than it is there. And so it's, the stresses are oriented to bond, okay? Now, how much strain can we do in a silicone, for instance? What do they say? How much strain can we go? 100%? Right? Our bond tests show that you can't pull it more than 25% before it starts pulling off the edges, which is kind of interesting. The other thing that's interesting, if there's any bit of moisture on there, you can go up to a certain amount, but then the moisture starts affecting it. They don't really know how to measure the moisture. And the other thing about the bond, if this is a dirty interface, it's not going to stick. So what do we do? This is a problem, okay? Is Richa here? She's my, yeah, Richa can tell you all about this. This is what she helped us do, is characterize the interface. And we did it with imaging. It's kind of interesting because the dirtier it is, the less undulations. And I think we can pick dirt up with this. And Richa worked with this system. We've since changed it, Richa, I'm sorry, but now we put it on wheels. Are you there? It's on wheels. And look, this is just that's just an iPhone. The imaging is really changing now. And there's a very good possibility we can see these under fill conditions. Now, think about a clean surface, clean and dirty by the imaging, you know, just by the imaging scale. We can get distributions, right? Clean and dirty. We can compare those and get a type 1, type 2. Isn't that fascinating? I showed this to the industry and I think it just froze them in their seats. They don't want to know this. Okay? If I could tell them, you know, a contractor wants type 1 air, owner wants type 2, right? That's what he's interested in. And I'm saying, look, this technology gives us the ability to characterize whether or not you're going to get bonding. We're not done with this, but we've done some field measures and we got some comparability of, you know, clean and dirty. But I think this is something we can do. We needed a better infiltration model than drip. Drip is kind of at least for concrete. This is a distributed infiltration. I changed it. This is mine. I put I use a weir orifice model to determine flow through a joint. So we did testing where we had to cut it away, but we widened and closed it to look at infiltration. And I just had to calibrate that coefficient right there. So we ran, you know, we just did very simple falling head tests over the joint. You know what's interesting on a test like this? There's a lot more infiltration out there than there is in here. I wonder why that is. Just things I just never really realized is going on with concrete pavements. But so yeah, so we worked out a function and we tried to keep all dimensionless units, which I think is key, to make sure units work out on these coefficients. Sometimes we don't, we forget, but we try to keep that in mind. So we use a probability prediction of the number of wet days. Inflow and outflow, what's the chance you're going to hold water, you know, in the interim? And right now with my modeling, I'm figuring more than 30 days is too much. 30 days out of the year. I wonder how often that happens. Probably, probably not. Okay. Okay, I got 10 minutes. Let me talk about bond here a little bit. So this is determined from FWD testing. So these are theoretical, bonded and unbonded. This is what we get from FWD. So we can calculate the degree of bond right off the test. Very easy and very convenient. And I have a hypothesis. The 1 minus that is the amount of erosion taking place. Okay? And I'm still trying to prove that a little bit. But let me just say something. This is my estimate of the strength right here. That's cohesive strength. That's the frictional strength. This is liftoff. I'm figuring if we lift off at the corner, we're going to lose most of the cohesion. The interesting thing I found on this strength, cohesion's everything. Once we get separation, we've lost it. And I don't know whether that's ever going to be healed. Maybe with an asphalt material you may heal it, I don't know. This is just a more circle representation of the shear strength. Is all. This is very simple. You see the phi angle here. And so, okay, so can we get the degree of bond? Yes, we can get that out of the FWD testing. This is on calibration, and I'm going to skip that because I'm about out of time. But here's my rework of the Hamburg device. So I'm sorry, I've now made it a concrete test, okay? But notice right here, here's my concrete cap. There's the base layer. And this thing works great. It is an awesome test. Look at the data we can get. And we can do that in 3 hours. A lot of data points. And this is an unbound material. Look right here. Look at that. An unbound layer. That's consolidation. Some type of consolidation effect. And this is the wearing from the Hamburg. And look at the differences here. Most of the voiding in unbound layers, I think, is this triaxial consolidation effect. I think that's a lot of it. What can we do with gradation to minimize that? That's my question. Can we change that with texture? Will that change? These are questions I have. And, you know, beyond that, it's not doing too bad for erosion. Okay? But anyway, we can calibrate to that. You know, we can work out calibration parameters. So the strength equation is degree of bond times the bond stress. And I'm getting both of these out of the FW. Why can I do that? Because we got multiple positions. They all have different contact. And so it gives us a range that we can come back and fit those parameters to. It's very interesting. Okay, very interesting. I think we can do this with FWD testing at, very, specific locations. I don't get a good estimate on that from the data. I'd like to, but this is really tied to the set in the slab, I think, right? So we can make a very interesting connection. Well, here is my calibration efforts, degree of bond. This is from the FWD. Here's the friction, and notice the intercept is going to be negative. This area here is where I'm calculating the erosion. So the blue line, the blue bar is the erosion on this section here. Got pretty good trend, just about what I thought it'd be, right? And then this is the effective thicknesses. This is a little off here, but that's what the calibration is involved here, is how effective thick it is. Now the effective thickness is the single slab combination of the base and the layer. The interesting thing is the degree of bond affects that, right? So when we model it, we can reduce and diminish that interface and come in the back door to calculate what that crack is. Because your slab gets thinner, the stresses go up, and then you can, you can calculate the crack. So in the modeling, we damage the interface, lowers the friction, reduces the thickness, and we reduce the K value. And by the way, Pavement ME does have it backwards on the K value, unfortunately. Okay, so we don't have that problem here because it goes the other way, the way you'd expect it to go down. But we get increase in stress, increased bending, loss of load transfer. So that's the process we go through to model it. And the damage curve, Barry, this is where I do the hydraulic wear. This is on this side right here. This is mechanical, so that's kind of the dormant, where you get the wear. Once you have the loose material, it just pumps like crazy, right? And so that's kind of what I'm hoping to model the damage is between mechanical wear and hydraulic pumping of it. This is based on velocity, viscosity, temperature. It's very interesting. I hope it works. We'll find out, I guess. But I've done some, preliminary model effects, and so far it looks promising. Anyway, so what am I getting at? We're going to put this in a software package, and we're going to put flexible design algorithms in it too. This is going to be what we think a transparent, open source design tool for academia. We need this. We need something we can share, a basis that we can share ideas. And this is what I want to tell you about. I hope that you'll take interest in it because we want your interest. We can set up input windows for inputs, and then we can do the model prediction. It's got to be simple, right?
That helps.
So what are the implications? This is my last slide, and I'm right on time, right, I think? So what are the implications? Joint sealants need to seal, absolutely. I don't know if we know how to do that. I talked to the industry folks about this, the International Groovers and Grinders folks. And I was talking to them about dirty joints, and they said, yeah, probably what happens is that guy that, that's cleaning this side of the joint, he doesn't get the other side. So he kind of walk away from it. And yeah, it's not going to bond. But monitoring and specification of quality, that's what we need to, I think about. Curing, it's only going to improve when we start adjusting it for weather conditions. Now, down in Florida, I hate to admit it, but I've been intimately involved with the test road. We're going to do a cured section, bad and good. Bad curing and good curing. And the first thing they asked me, how are you going to do that? Okay. And I said, it's easy. We can't predict the weather, right? But we can monitor it. If the wind speed changes, if the evaporative conditions change, we can monitor that. So we set up a table of speed for the curing machine. We covered all the ranges that we expect to see based on historical data, okay? They got one control on that machine. It's a lever. It goes like this here. one control. We're gonna run that machine off of the side. We're gonna measure the time and distance and figure out what that speed of travel is and where that handle notches in. And that's what we'll do. We'll just tell the guy, look, the wind's picking up. It'll probably be the same each day, I think. We'll just adjust that handle a little bit and let him go. At least get a uniform, supposedly, an application rate that fits the wind speed. Now, it's still a dozen nozzles across 20 feet or whatever. I don't know how that's gonna work. That could run it all. But anyway, uniformly applied, yeah, okay, we gotta figure that one out. Erosion is not a standalone stretch type, and this is unfortunate because that's how everybody treats it. And it actually is integrated into the cracking process. That's why we need to do it. Lastly, yes, we need a design tool that we can have. Okay, that's my message. I appreciate your time. I hope it. Anybody have any comment, any observations? I'd love to hear them.
I enjoyed very much. Excellent presentation, thanks. When you talked about the erosion model, I know a few years ago when I teamed up with Jeff and we were writing a proposal for the 1-53.
Yeah.
Eventually, I think Bob got that one to work on it. But your erosion model you mentioned about was probably the best thing out there that's been done, looking at erosion aspects and foundation support requirements for slabs and concrete. I was wondering if Bob brought that model into the 1-53 work. I know the report is supposed to come out.
He's worked on the calibration, the form of the calibration. And he also is helped a little bit with the unbound characteristics. Now, I think you're familiar with the tests. And I attempted to follow that regimen. We ran out of steam trying to do that. And I went in his office one day and I told him that. I don't know if he wanted to hear that, but I said it didn't work out. And I said, why can't we just take the Hamburg curve and get it out of that? And he started thinking about it. He says, yeah. Now, it's not as good as the rigorous method, but nonetheless, he thought that we could do that. And so that's where I am with it, is to try, and that, that's going to depend on the amount of, cementitious material and so forth, right? So, yeah, there's some things there.
So some of that will come in the 1-53 reports?
No, probably not, but it got things started. I mean, I'm now into it, so I'll see where it ends up. It's an interesting thought, I think. Yes, sir.
Okay, we've got some pavements now going down with, short, small slab stuff, 4x4s, things like that. And you wind up with a whole pot full of cracks because you saw them in there, right? How would you surmise they're going to do in the future? They're not sealed, right? It rises a little bumpy, but
I suspect they're not sealed. Yeah. Well, you could seal them, I suppose, because very close to interval, the seal strain ought to be minimal. That'd be a good candidate, but the thing is, Marshall, the more of that stuff you put in, the higher the probability goes that you're going to have something. And then they don't account for that either. And that, I'm intending to somehow figure that out for this. The number of possibilities that you could have something go wrong, that has to fit in the equation. But I don't think that idea is that technology is going to make it. It's just going to be too expensive to maintain it. I mean, they get a lot of corner breaks and things. And, that's just reminiscent of the problem, But I guess we'll see. Well, I appreciate everyone's interest. I hope
So
that.
if there's no more questions.
Thank you. I think there's more pizza left. Finish that up. Where it going?
So much fun.
Thank you. Very good.
Good, hey, you're keeping your leg around the clock there. Hey, you do, the other. Good point.
But your ribs and all.
More like next month. And then one day suddenly you get an email saying, hey, can you do all this stuff?
You know, you got an open.
Yeah, well,
8 inches thick, 12 years old.
But my point is, they designed it as a composition. They're saying, hey, your big point is got this E and this and all that crap.
well, that doesn't happen.
No, Marshall likes it.
Stiff on stiff, man, they thought that's gonna last forever.
I'm not sure whether I'm sure you know about that. This is like this
You know, we
they
tried.
have a more.